following notes are for Unit 2 on acceleration. These are supplemental notes, so make sure you print out the copy of these notes that are fill in the blank and fill them in as you go along. So this chapter is all about acceleration. Of course, acceleration is when the velocity of an object is not constant, right, or its velocity changes over time. So a typical equation that you'd see in a textbook is A equals delta V over T. In our lab, we basically came up with this equation. It just looked a little bit different, but you can have that written down on a note card or formula sheet. That might be useful for you during notes. So it says acceleration is a vector quantity, just like velocity. We really haven't gone into vectors, but what that basically means is it's like velocity. It has magnitude and direction. So it's not only just a number, but it also is, are you accelerating to the right or to the left or north or south or whatever it is. So two example problems here. A plane goes from rest to a speed of 65.28 meters per second in 15 seconds. Find the acceleration. Well, using that equation that was above, right, if the plane goes from rest to a speed of 65.28, that is your change in velocity. Now your change in velocity needs to be final minus initial. So in this case, your final velocity would be 65.28, your initial would be 0, and of course it happens in 15 seconds. So you simply plug those numbers in and you get your acceleration. Now it's important that you're careful with the signs of things. Like the 65.28 meters per second, we left that as a positive value and we were getting faster, so our acceleration also came out to be positive. If it was the other way around, if it said the plane was going 65.28 meters per second and then stopped in 15 seconds, well, now your delta V would have ended up being a negative value because it would have been final minus initial, and then your acceleration would be negative. And then looking at all those values, you would see that your 65.28 would still be a positive number, but your acceleration would be negative, meaning you were slowing down. So moving on to number 2. A car slows from 85.5 meters per second to a speed of 33.2 meters per second in 1.25 seconds. So now you have to take your final velocity and subtract your initial velocity using the same equation, but it's not just going to be the difference. It has to be final minus initial. So 33.2 minus 85.5, and then divide it by the time. So this negative acceleration here is showing you that it's slowing down, and you only know it's slowing down because your other velocities, initial and final, were both positive velocities. You could have chosen to make the 85.5 and the 33.2 negative velocities. Your acceleration then would have come out to be positive, and the key there is they would have been opposite signs. And when you have velocities and accelerations that are in opposite signs, that means that the object is slowing down. This is just a quick little review from what we were doing last time in Unit 1. I know the graph up here says y, but think of it as our displacement in x. It says that the graph has a slope from A to B. From B to C the slope is 0, and then from C to D we have a slope again. So if we wanted to find the velocity from 9 to 14 seconds, right, from 9 to 14, well, because it's a constant slope, it would be a constant a constant velocity. So you could just find the slope, right? Rise over run. You start at 4 and you go up to 8. So your rise would be 4 and your run would be the difference in time, and that would get you your velocity. Now if you wanted to find the average velocity, well, now that's a little different, right? You could on the graph draw a straight line from A, I know that doesn't look straight, but from A to D, and if you found the slope of that line, it would give you your average velocity, which is what this work is showing. Right, your delta x essentially is the rise of that line that I drew in, and your run would be the time of that line that I drew in. So calculating rise over run is essentially finding your total change in position and dividing it by your total time. Again, review from last unit. Now looking at this position versus time graph, this is more what we're seeing in this unit with acceleration. Our position versus time graph no longer is steady slopes. The slope is constantly changing. So from A to B, the slope was constantly getting flatter, so it was slowing down. And from B, it looks like to D, it was getting steeper, which means the object was getting faster. And from D to F, our slope was flattening out, so it was slowing down. So we were constantly changing velocity, and some points we were getting faster and some points we were getting slower. So it says the average velocity is the slope of the line connecting points A to B, D, E, or F. So if I found this line here from A to B, that would give me the average velocity, because again, it would be your change in position over your change in time. If I wanted to find the average velocity from A to D, I would just like before, it doesn't matter that it's curving, connect those 2 points, find the slope of the line. It says the slope of the dashed line at each point represents the instantaneous velocity, right? That's the tangent point. That's what we did in the lab. If you had to find that from a graph, it says you could extend the line to make it larger in order to find the rise and the run. So, you know, they're trying to show an example here in green, but let's say I needed to find the, velocity at point C. I would try to take that line, and I know I'm not drawing a straight line, but draw a large tangent line and then try to find points that you could estimate or calculate out, and then I could do the rise over run for that slope to find the instantaneous velocity. Another example, number 5, a train moves slowly along a straight portion of a track. According to the graph of position versus time, find the average velocity for the total trip. So this whole line in here, to A, to B, to C, is your change in position over time. So you can see from the origin to A, the object was moving, or the train was moving at a constant speed because it's a constant slope. A to B, it had no slope, so it was stopping. But from B to C, that slope slowly increased and got steeper, so that means that it was moving faster and faster. All you have to do to find the average, same thing as before. Rise over run. Connect the beginning and the point that you're concerned about and find that rise over run in order to find the average velocity. So the average velocity over that 12-second interval would be 0.83 meters per second. Part B says find the velocity during the first 4 seconds. So during the first 4 seconds, well, that's easy. It's a constant velocity because it's a constant slope. So you're just going to find the slope of that line. Part C, the velocity during the next 4 seconds. So from 4 to 8 seconds, well, the slope of this line is 0, therefore it has a velocity of 0. Part D, the instantaneous velocity at 2 seconds. Well, the instantaneous velocity at 2 seconds, everywhere from 0 to 4 seconds had a constant slope, which means every place from 0 to 4 seconds was moving at a constant velocity. Therefore, the slope from 0 to 4 is the same everywhere, which means the instantaneous velocity at 2 seconds is the same as it would be at 1 second or 3 seconds or 0.5 seconds or 3.5 seconds, because everywhere has the same slope. So that is 1 meters per second, right, if we calculate out that slope. The last part, part E, the instantaneous velocity at 9 seconds. So at 9 seconds, that's this green line. I'm trying to extend my tangent line, right? So if this is the slope at that point, the slope of that tangent point, I'm extending it. I can pick any 2 points and try to figure out what it is. So I picked, right, an ending position of 4.4 4.5 and a starting of 0. So you can see if I'm here at like 3 seconds, right, my 3 seconds, then I went up roughly 4.5, it looked like, right, when I got to 9 seconds. So it's a little bit of estimate, but at least it gives me an idea of what the instantaneous velocity is at 9 seconds. Number 6. This time we're looking at a velocity versus time graph. During a baseball game, a player runs after a fly ball. What is the player's acceleration from A to B, B to C, and C to D? Well, looking at this graph, the first thing that happens is people look at it and they don't pay attention to the fact that it's velocity, right, not position. So the fact that it's a velocity versus time graph, nothing in here, not on the y-axis and not on the x-axis, none of this is position. The only thing that shows me position is the area under the curve. So I would have to calculate out all of this area in here if I wanted to know the change in position. Well, the acceleration, though, that's the slope of the line. So from A to B, there's a constant slope, so there was a constant positive acceleration because it's a constant positive slope. So I can find my rise, right, my final velocity minus my initial velocity. So I ended at a velocity of 4, I started at a velocity of 0, and it happened in 2 seconds. From B to C, right, the slope is 0, so the acceleration is 0, right? Looking down, right, the slope in here is 0, so the acceleration is 0. And then the last part, I just want to calculate out this slope, which is going to be negative. So again, rise over run, and now my acceleration is negative in this case. So all of those velocities were positive if you look back at that graph, but the acceleration is negative because the velocities are positive and the acceleration is negative. It means it was slowing down. Okay, number 7. Using this graph, find A, the velocity from the start to A, the velocity from A to B, the velocity from B to C, etc. Well, looking at this graph, right, this is a position versus time graph, which means if I want to find the velocity, all I have to do for each of these instances is find the slope. So all of these were just calculating out the slope for each one, right? From the origin to A, I went 4 meters in 3 seconds, so 4 divided by 3, right? From A to B, the slope was 0. Now I went from 4 to, it looks like 8, so I rose 4 in 1, 2, 3 seconds. So again, 4 over 3 is 1.2, etc. Finding the displacement, remember, displacement is not distance traveled. I don't want to add up 4, add up another 4, and then add up whatever this happens to be. I want the displacement, so the initial position and the final position. I ended at a final position of -5, and I started at 0, so final minus initial, so -5 minus 0 divided by the total time of 15 seconds should get you the displacement. Oh, sorry, part F says find the displacement after 7 seconds, so that would be, I started at 0, and at 7 seconds I'm roughly here, so I was estimating that as 5.3. Last thing, part G, make a velocity versus time graph. Well, if these are the velocities, then all you have to do is plot those points. Right, it was 1.3 meters per second for 3 seconds. And so for each graph, the next one I was 0 meters per second up through 6 seconds. Right, the next one I was 1.3, so from 6 to 9, I was going 3 again. So for each one, you're just plotting. For D to from C to D and D to E, they both had the same slope of -2. So during that whole time span, you had a negative velocity. If I calculated out the area under the curve here and here, I would have came up with the same 5.3, hopefully. Moving on. Okay, if a body is undergoing a constant acceleration, we can analyze the motion and come up with several equations that we describe that will describe the motion. So this was that equation we were looking at earlier. This is the equation we had from the slope of the line of a v versus t graph. So it's two ways of looking at the same equation. So that's one equation. Right, two more equations. We had this one from the area under the curve of a v versus t graph. But remember, you don't see it that way much. A lot of times this XO will be moved over and you'll have delta x here instead of x final and x initial. And then the last one, right, this is one we were combining a bunch of equations together to get this one. Those are the three main equations that you're going to use, and these following examples are just using those equations. So number 8, a car undergoes an average acceleration of 3.55 meters per second. If the car is accelerated for 8.5 seconds, how far has the car traveled? So if the car undergoes an average acceleration of 3.5, we know acceleration. The car is accelerated for 8.5 seconds, so we have a time. And how far has it traveled? So if we're looking at it, we're going to pick basically this equation where we're going to say it starts from rest, right? And we can pick the origin wherever we want, so we could pick the origin where we started, and so we end up with that equation. Now it's just plug in your numbers and calculate your answer. I knew to pick that equation because I was looking for, out of my three choices, an equation that had acceleration, which they all do, an equation that has time, which now I've limited it. This one over here does not have time, so I wouldn't use that one. And then how far has it traveled? I want an equation that has x in it. Well, this one doesn't have time, so I can't use that one. And the previous one, right, from the slope of the line, doesn't have position, so I can't use that one, which leaves me to this equation that I used. So I use that same process for all of the problems. Number 9, a truck undergoes average acceleration of 2.5 as it speeds up. If it starts from rest, so we know the initial velocity and the acceleration, and accelerates for a distance of 875 meters, how fast is it now going? So we know the acceleration, we know the initial velocity starts from rest, right? We know a distance, or a change in position, is 875, and how fast is it moving? So now we need an equation with a final velocity in it. We can't use this equation, it doesn't have final velocity. This equation does have final velocity, as well as the other one, but this equation has our change in position, so you know to use this one instead of the other equation, because that one has final velocity, initial velocity, acceleration, and time, and we don't know anything about the time. If you saw a different equation there, your mind wasn't playing tricks on you, there was a mistake. Anyways, so looking at the equation that we were talking about, now you're just plugging in your numbers. Remember, you can say that you started at the origin, so your final position was 875, so 875 minus 0 is your change in position. Don't forget to take the square root of your 2 times 2.5 times 875, and when you take the square root of that, it gets you your answer. So you were going 66, or the truck was going 66.14 meters per second after it was after it went 875 meters. Now you could have chose to make this 875 negative, but if you were moving in the negative direction and you started from rest, then you would have had to accelerate in the negative direction. And this answer here, because it's squared, it still would have come up 66.14, but you would need to realize that, okay, well, everything was moving in the negative direction. You would have to go back and assign a negative value to it, so it can make it kind of tricky. Let's see, a typical jet lands at a speed of 160 miles per hour. 1 mile per hour is 0.447 meters per second. It deaccelerates at a rate of 10 miles per hour per second. If the plane travels at a constant speed of 160 miles per hour for 1 second after landing before applying the brakes, what is the total displacement of the aircraft between touchdown on the runway and coming to a stop? So this one's complicated because you have two different types of motion. For 1 second, you were moving at a constant speed, and then for all the rest of the time, you were slowing down at 10 mile per hour per second. Well, the first thing is we're in miles per hour, we're in miles per hour per second, and we're in seconds. We need everything to match up. We can't have hours and seconds and hours and seconds. We've got to get everything in the standard in the same units. So I'm going to convert everything into meters per second squared, and seconds. Right, so if 160 miles per hour, if 1 mile per hour is 0.447 meters per second, I put the mile per hour on the bottom so that these units will cancel. So 160 times 0.447 is 71.52. So I know that's the velocity that you were traveling at during this 1 second, or that's your initial velocity when you started to accelerate. Now the 10 meters per second, or sorry, miles per hour per second, I need to be in meters per second. So if it's 10 miles per hour per second, I need to convert this miles per hour again. So just like before, mile per hour cancels. I'm in now meters per second, which is meters per second squared. Now if I'm making this initial velocity a positive 71.52, then the acceleration has to be negative, so that means that you are slowing down, not speeding up. So moving on to the next part, right? My second step, I'm going to look at just when I was moving at a constant velocity. So you were moving at 160 miles per hour or 71.52 meters per second for 1 second. So using our equation for moving at a constant velocity, right, delta x equals vt from unit 1, you're moving at that 71 for 1 second, so you travel 71.52 meters in that airplane when you're moving at a constant speed. Now we need to figure out what happens when you start to slow down. So looking, right, we know that initially when we hit the brakes, we're moving at 71.52 meters per second. We know our acceleration, right? We converted this 10 into negative 4.47, so we know the acceleration. We're looking for how far, and of course we're stopping. So if we're going to come to a stop, then the final velocity is 0. So that gets us our change in position while the plane was accelerating. So the plane went 572 when it was accelerating and 71.52 when it was going at a constant speed. Adding those two together will get you the total change in position, or the total distance traveled in this case. So the airplane went 643.68 meters down the runway. Last example, a car traveling at a constant speed of 24 meters per second passes a trooper hidden behind a billboard. 1 second after the speeding car passes the billboard, the trooper sets off in chase with an acceleration of 3 meters per second, so the trooper is at rest. How long does it take the trooper to overtake the speeding car? And part B, how fast is the trooper going at this time? This is kind of like the problem where in the previous chapter it was the two objects were moving towards each other. The one car was chasing another, and where did they catch up? So it's very similar to that, except for now we have one car going at a constant speed, so we've got to use delta x equals vt, or because they're not going to travel the same distances, we want to take that delta x and make it x equals vt plus x initial, and then the trooper who's accelerating. So we've got to consider both of those together. Now, it says that 1 second after the speeding car passes the billboard, the trooper sets off. Well, during that 1 second, how far is he going to travel? That car traveling at 24 meters per second is going to go 24 meters in a second. Right? So at T1, when the trooper starts, that's really when we're going to say is the initial time. So because of that, we're going to say our car doesn't start at the origin. We could set the trooper as the origin or the position of 0 and say that the car starts at a position of 24 meters because it had that extra second to travel. So taking that delta x equals vt, again, we really don't want to use the delta x because they're not going to travel the same position, and the little sub c stands for car. We want to use this one, right, where the final position of the car equals, before we would always put vt plus xo. So using this equation, right, the car is going to start at a position of 24 meters because it had that second to go before the cop goes, and then he's moving at a speed of 24 meters per second. Well, the police officer, the trooper, right, if we want these to be the same, right, we want this trooper to catch up to this car. So their final positions, if we make where the trooper sets off as the origin, this guy is 24 meters ahead of the trooper, or at a position of 24 meters. This guy is at the origin. And so we can kind of look at these two equations as setting them equal to each other because we want them to be at the same position again. So filling it in with the trooper, right, the initial velocity of the trooper is also 0. So we can get rid of that, which leaves us our 1/2, our acceleration of 3 times our time. Well, the time that both of them are going to travel is going to be identical because we placed this car 24 meters ahead of the trooper. So both xt and xc are equal to each other, therefore we can set them equal to each other. So the 24 plus 24t is for the car, the 1.5t squared is for the trooper, and we can go through, right? We've got a t squared, a t, and a 24 using the quadratic equation. Plug in all your values, right? So we're at 1.5. We move the 24t over, so we get negative 24t, so that's why you've got these negative 24s in here. We would take this 24 and add it over. That would be another negative 24, and that is this negative 24, right? Because it's negative b plus or minus the square root of b squared minus 4ac over 2a. So punching that in, you get two different times. You will get a negative time. Well, you can't go back in time. Therefore, the time it takes for the car and the trooper, or the trooper, to catch up to the car is the 16.94 seconds. And then the last part, part B, how fast is the trooper going? Well, now that you know this time, you can take it and you can either plug it into here or plug it in to here, because either way it equals the final position that we're looking for. That would be to find the position. Oh, sorry, it wants to know how fast is the trooper going. If you wanted to know the position, you'd plug in the time and you could find that position that they catch up to each other. But part B wants to know how fast is the trooper going. Well, we know that he started from rest. He had an acceleration of positive 3, and he traveled for a time that we've just figured out is 16.94 seconds. So we can solve for that final velocity of the trooper, 50.82 meters per second. So hopefully this helped. I know it was fast. Obviously you can rewind and listen to it over again, but it gives you a couple extra example problems to look at with some explanations and some notes in writing that might be helpful also.